Alright, today I'm going to start talking about quadratic functions. During the presentation, I'm going to do a few warm-up problems, just a few review questions. So, a while ago we learned about whether or not a function is linear, and we learned to explain that. We can tell if something's linear if it is increasing by a constant amount. So on this side you can see the x is increasing by a constant amount of 1. Now in order for this to be linear, the same thing has to hold true on the other side. It doesn't have to be increased by 1, but it has to be a constant amount the whole way through. So from negative 9 to negative 2 is a positive 7, and from negative 2 to 5 is a positive 7. And then we have another positive 7 and another positive 7. So this one is linear. And the reason being is that both the x and y values are increasing at a constant amount. The other thing we want to review today is finding the domain of a function. And actually, for this, they actually give me the domain, so we're not quite to finding the domain and range and reviewing that. But what we're going to do is generate the ordered pairs given this domain. So I'll go ahead and put in negative 2, negative 1, 0, 1, and 2. And then what I can do to find the y values is just simply plug those in. So I'd have 3 times negative 2 plus 2. That would be negative 6 plus 2, which would be a negative 4. Then I do it again with the negative 1. And I'd say 3 times negative 1 plus 2, which is negative 3 plus 2. That's negative 1. Then I plug in the 0. Well, 0 times anything is 0 plus 2 is 2. Then I plug in the 1. 3 times 1 plus 2. That's 3 plus 2, which is 5. And then the last one, plug in the 2. 2 times 3 is 6. Plus 2 is 8. So 3 times 2 plus 2. 6 plus 2 is 8. So these would be my ordered pairs. Negative 2, negative 4, negative 1, 0, 2, 1, 5, and 2, 8. The other part of review I would like to talk about is stating the domain and range. The domain is the x values, so the domain of this function is negative 2, negative 1, 0, 1, and 2. And the range is the y values, and so it's negative 9, negative 2, 5, 12, and 19. Now I really should say y equals these amounts, and this should say x equals those amounts. Domain is x and range is y. Okay, what we're going to be doing, first of all, is using a table of values to graph a function. So you do that in the same manner you do with your linear functions, where you just take the negative 2 and you plug it in. So what we're really saying we have is y equals negative 2 squared, and the negative is being squared as well, so we get 4. Then we're going to plug in negative 1, y equals negative 1 squared, which is 1. Then we're going to plug in 0, 0 squared is 0. Then we're going to plug in the 1, 1 squared is 1, and then plug in 2, and we get 4. Graphing these ordered pairs, I get negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. You can graph any equation that's given to you by picking points and plotting them. That always works. The next thing we'll start talking about is how we want to notice that the graph is not linear. A linear function makes a straight line. This is called a quadratic function, and a quadratic function is what we've been seeing, that ax squared plus bx plus c. Really, it just needs to have the x squared term. So there has to be an x squared term. That's why it says a cannot be equal to 0, because if this was 0, there would be no x squared term. I would like you to know the word parabola. The graph of a quadratic function is called a parabola. Okay, on the next part of the videos, we're going to determine whether something is a quadratic function or not. Alright, for this next part, the directions say tell whether the function is quadratic and explain. I think one of the easiest ways, there are other ways to figure out if something is a quadratic or not. You can look for the second difference. but honestly, I think you guys will find it easier just to go ahead and graph it. So you got -2, -9, -1, -2, 0, -1. You've got 1, 0, and you've got 2, 7. You can see this is not a quadratic. It does not make a U or a hill, which is what a parabola would make. We need this type of shape for it to be quadratic, one of these two. The next one, to tell whether or not something is a quadratic function, we'll just go ahead and graph these points that are given. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Notice what I get is the parabola shape, so this is a quadratic because I do get the parabola shape. The next part, it does not give me a picture anymore of what does not give me a picture or points to go off of. I could create points, or I can remember what I learned earlier, that a quadratic function is in the form of y equals ax squared plus bx plus c. As long as I have this x squared term, I know it's a quadratic. Otherwise, it's not. This does not have an x squared term, so this is not a quadratic. This happens to be a linear function. Okay, so you can say the reason is no x squared term. On my next example, if I look at this, I could put it in that typical ax plus bx, ax squared plus bx squared, or excuse me, I keep saying it wrong, ax squared plus, there is no bx, plus c, to see whether or not it's quadratic. But I really don't even need to do that necessarily because there is only one x squared term, and since there is an x squared term, it is a quadratic. So this is a quadratic because there is an x squared term. Another example of that, again, it's very simple, that this is a quadratic, and the reason again is that there is an x squared term. Alright, for my next example, it says, use a table of values to graph the quadratic functions. And then it asks some other questions. So what can I pick for x's? Whatever I went ahead, I always make sure I pick some negative and some positive values. I try to just go in order to make sure I'm going to get that U shape. So this one, when we plug it in, we have to be very careful though, because it says -4 times -2 squared. So the -2 is being squared, okay, which gives me a 4, but then I'm still multiplying by a -4. So my actual y value happens to be a -16. So then when I go to plug in the -1, I have y equals -4 times -1 squared. Well, the -1 is being squared, but I'm still multiplying by -4. So -4 times 1 is -4. Then when I plug in 0, I just get 0. When I plug in the 1, I have y equals -4 times 1 squared. Okay, well that ends up being a 1, and then times -4 is -4. And the same thing occurs when I plug in my 2. I'll end up with the same answer up here as -16. So I'll graph these points. -2, -16 is way down here. -1, -4 is right here. 0, 0, 1, -4 is here, and 2, -16 is way below. Okay, so what is the domain? I may have to do that on the next video, but I will go and address the vertex. This is the vertex. The vertex is its highest or lowest point of the parabola, and the vertex on this problem happens to be 0, 0. I'll continue this on the next video. Okay, where I left off was I hadn't answered the question, what is the domain and what is the range for this particular problem? So I will go ahead and answer that the domain is all the x values. This function, even though it's very, very skinny, will reach all the x values if you go way, way far down below. And parabolas are always going to have the domain of all reals. So all reals means all the x values are going to work. The range value is the y values. Now notice that the highest point the y can go is 0 or below. There's not a 1 or a 2 or anything like that. So 0 is a significant number. It's the highest amount it can go. Y is not bigger than 0. It is less than 0 or it is equal to 0, and that's how we're going to describe the range. Range is how far up and down we can go. Domain, how far right and left we can go. What I did mention to you in the last video is the word vertex. It's the maximum or the minimum of each function. Notice the vertex in this problem was that 0, 0. So it's the max or min of each problem. What determines if a parabola opens up or down? Well, it's that a value in your y equals ax squared plus bx plus c. If this a is positive, so if it's positive, it opens up, it opens like this, and there's a minimum value. If that a is negative, then it goes down and it has a maximum value. Alright, so what we're going to do is we're just going to quick answer these questions. These are pretty simple. We're going to first make it into the form y equals ax squared plus bx plus c. So we've got y equals ax squared plus bx plus c. There's my values. And if I look right here is my a value. It's the one that's attached to the x squared. A is greater than 0, so that means that it opens upward, which means it looks like this, and it means it has a minimum value. Right there is its lowest point. Let's try another one. This is not quite in the right form. I'll go ahead and just rewrite this. It's all on the right-hand side, but I'll just rearrange these. Ax squared plus bx, and then there is no c, that's fine. Here's my a value. A is less than 0. So when a is less than 0, I know that it opens down. So that means it looks like this, and it means it has a maximum value. Looking at a couple more of these, I have, this is right here, I have my a value. My a is less than 0, so I know it's opening down, it's downward, and downward looks like this, so it has a maximum value. This last one, it has an x cubed in it, so it's not even a quadratic function. So this is not even a quadratic. It doesn't have an x squared term. Okay, this next we're going to be doing is we're going to identify the vertex and then say whether it's a max or min. So the vertex is always the lowest point here. So if you look at this point right here, we have -3, +2. That would happen to be a minimum. Here we have 2, 5. That's the vertex. 2, 5. And this one happens to be a maximum. Okay, let's take this just a bit further. And let's go ahead and find the vertex. The vertex here would be -6, -3. The domain is all reals. Remember, parabolas are going to have all reals. This happens to be a maximum value, okay, and the maximum value, this is the max. We'll just go ahead and say the maximum is -6, -3. The range is how far up and down it goes. So remember, this is a significant value because it's not going to go any higher than this, so -3 is significant, and it says y has to be less than or equal to -3. Alright, this is the last video for this section. This is just a longer section. There's a lot of new vocab and such in there. So what we're going to do is finish this up with just these last two examples. I'll go ahead and tell you the vertex again. So the vertex is -2, -4. We're now going to answer the question of the domain. Domains for parabolas are all reals. It's how far right and how far left it goes. There are no bad values. It will reach far and left, or left and right as far as reachable, as far as it possibly can. So that happens to be all reals. This is a minimum value, and we will go ahead and tell what the minimum value is. The minimum value happens to be -4. On the last video, I probably should fix that. I went ahead and put the entire ordered pair, but really the maximum value is just the -3. So we'll go ahead and change that. It's just the -3. And on this one here, then the range is how far up and down it goes. Notice that this is the lowest point it's going to be. So -4 is significant. And what we're going to say is that y isn't less than -4. It's greater than or equal to -4. In this last problem, I have this picture given, and this picture has the point of 2, 3. So it has a vertex 2, 3. It has a domain of all reals. It has a maximum value, and that maximum value occurs at 3. The 3 then is significant for the range. The y is no bigger than 3, so it's going to be less than or equal to 3.